Thank you. I hope you are having a wonderful conference. We're really excited to be here to present this performance quiz. So we did it a few times in Python already and in other languages, but we're really excited to do this one in Rust, and we hope you will get some interesting findings. Maybe just to start, with, we have a bit of context on us. So, as mentioned, we are the founders of CodeSpeed. We are based in France, so we're really excited as well to have EuroRust here in Paris this year. And we've been working on CodeSpeed for a bit more than 2 years now, and we are really excited to share some learnings we had and some interesting facts about performance. But before starting, just a bit of context on why performance matters. Probably you already know this, but I think it's good we think about why this will be interesting in a day-to-day life developing new software. So the first kind of pro of performance is that actually drives a better user experience and as well more revenue, because if you have a better experience, you're more prone to just use a product and keep using it, which makes a better user experience overall. And as well, it's a feature. And for example, if we take the Astral performance tool, Astral Python tooling, it has been widely adopted in the Python ecosystem. So it's built in Rust, but adopted in the Python ecosystem, mostly because of performance compared to the previous tooling. So here, performance is just a feature and made the difference between with other tools. And then we have as well the cost savings, obviously, because if your software is faster, you can run more of this software on a single instance, and then it's cheaper to run. And this gives better sustainability of software, which is good for data center carbon footprint, for example. And now this matters even more today, more than 10 or 20 years ago, because today, the single core performance and more broadly just CPU performance and compute performance is starting to reach a hardware limit and just a physical limitation. So there are some new research and stuff to overcome those limitations. But so far, we are not following Moore's law anymore. And basically, we're just capped. And on the other hand, so basically what you have on the right, the computational demand is increasing. And this doesn't even include all the LLM models and other transformers models, which take even more parameters and consume even more energy to train.
Yeah, but so performance is important, but getting performance right is really hard. We are not machines as much as we would like to, and even the best performance experts will get things wrong when they take a look at a piece of code. So it's something that's really hard, and that's what we want to try today. So as we said earlier, if you don't trust us yet, we'll put you to the test. So there is a QR code that you can scan to join the quiz. So how it works is that we'll have a few questions throughout the talk. So you don't have to stay on your phones. We'll tell you when you have to look at your phone, so don't be stressed. Still listen to what we're going to say. We'll leave the QR code on the left, it should work. So there will be a leaderboard. You'll be ranked, and the winner will get a prize. So be sure to, we'll try to see who won at the end. To gain points, you need to have correct answer, so the right answer, and you need to answer fast. So the faster you answer a correct answer, you will get more points. And as I said, we'll tell you every time there is a question, so be sure to still listen to us. About the measurement, so for each of the questions, we'll show you two versions of an algorithm, and we'll ask you which is the fastest. Or, we'll ask you which is the fastest, or if each of them are the similar performance with a margin of more or less 10%. These benchmarks were run on with Rust 180 on a bare metal instance with 16 scores on x86. We're using the profile release for those benchmarks. That's about it for the method of the measurement, and I leave to Arthur for the first question.
And so we are using release profile except for the first example, like the warm-up question. And as well, as Adrien mentioned, it will run on a x86-64 CPU, and this should be enough. There will be no edge cases on the CPU, the exact CPU model or stuff like this. This is really not the goal of this talk. And so the first example and the first case study we'll do is basically try to measure the impact of a release profile versus a debug profile. So you probably heard of it, and you know that basically in your cargo toml and mostly in your Rust project, you can configure the profile that will be used to build your code. And actually, you can also choose the profile that will be used to build your benchmark. So by default, this cargo bench command to run benchmarks uses the bench profile. But here we put it explicitly. So on this algorithm, which is a bubble sort, like really simple implementation, nothing really exceptional, which profile will be the fastest. And so yeah, you can see here the actual profile highlighted. And so now we can start the actual first question. So we'll get 25 seconds to answer to this question. And we'll get all the results at the end. After those 25 seconds. For the next questions, we are going to have only 10 seconds, so we can cover more topics. And as well, we don't have to wait that much. So which is the fastest, either the dev profile or the bench profile, or maybe the performance is the same for a bubble sort algorithm. And time is up. And so you got it right. So 9 people thought it was a dev profile, 21 that basically performance was the same, and actually the bench profile was the fastest. So actually when we run the benches, here is the difference we can observe. So we're going to use those charts, those bar charts for all the answers. And the idea is that it represents the execution time. So the smaller the bar, the better the solution, basically. So here we can see that the bench profile is really small compared to the dev profile, something less than 1 millisecond against 13 milliseconds. And why? This is mostly due to the fact of the differences between those profiles. So on the left, the dev profile have an optimization level of 0 against an optimization level of 3 for the release profile, which basically the release profile is like the bench profile is built from the release profile, so it's mostly the same. And so yeah, what makes most of the difference here is just the optimization level. So when you run your code and you want to see actually how it will perform, using a release profile is extremely important, because otherwise you're not really comparing some things that will happen in production. However, as noted down on the top bottom left, it will incur some longer build times, which might be an issue if you're just developing and you just want to iterate faster and run some tests without having to care about measuring performance. But when measuring performance, this is really critical. So now off to a new example.
Yeah, so our first real example, so we are going to compare two implementations of the same algorithm. The algorithm is pretty dead simple. We are going to multiply a variable x, which is a U64, and we are going to multiply it by 2 to the power of y, and here y is a const. So the first is going to use the pow function on U64, and the second one is going to use bit shifting, where we're going to shift the bits of x to of y elements. So same as before, we're going to ask the question. So now you have only 10 seconds to answer. Which is the fastest, or are they the same? Yeah, it's pretty interesting. So yeah, it was kind of a dead heat between same performance and the shift left is faster. So it's one of the first myths that we want to break, is that even though using bit shift is pretty fancy and looks cool, it doesn't really matter, because the performance is completely the same. It's exactly the same. So you look cool if you write use bit shift, but it doesn't really matter. So let's dive a bit deeper to understand why. So it's a pretty simple view of the Rust compilation pipeline. So we start with Rust code, then Rust C compiles that to LLVM ER, and then LLVM transforms that into assembly, and we'll stop at assembly because that's what we are going to look at, so the code that the machine is actually executing. So let's look for this specific code, what the Rust code looks like and the assembly looks like. And when we take a look with the release profile, we can see that both implementations of the Rust code, they have the exact same assembly representation. It's down to the instruction, to the character. It's exactly the same. So why? So that explains why it's the same performance. But why do we have the same code? If we take a look at the POW function implementation, we notice that POW is a const function. Const is defined with const fn. So here what we have is constant evaluation. So basically, when we define a function with const, if the parameter we give to this function is itself a const, then the compiler will be able to directly process the function itself and compute the results during the compilation time. So that's why for this specific case, since the parameter we pass to POW is a const, the compiler was able to actually just execute the function. So the learning here is to make sure to use const when it makes sense to enable those kind of optimizations. Another example that we are going to take a look at is this kind of similar to the one that we had before, but now if you take a look closely, we change a bit the implementations. Now y is not a const, but it's a parameter that can vary. So we are going to ask the same question, which is fastest, mul_pow or mul_shift_left, without the const. Stuck. Okay. It's kind of the same results, but with the explanation most of you got right. So yeah, now shift left is faster. Not that much, but still a bit, quite a bit faster. And to understand, we'll still take a look at the corresponding assembly code. And now we can see that the assembly code is indeed different because the optimization that we talked about was only possible with the const parameter. Now we can see that there is a lot more instructions in the assembly and especially a loop in the assembly code. So it will take way longer to execute this code. All right. And now we can move on to the next one.
Like a continuation of these powers, but this time we'll compare basically writing just handwritten multiplications and using a for loop to do the multiplication as well. So basically what we want to do is to build a function that will put its input to the power of 10. And so which one will be the fastest? The one using an accumulator and a loop and returning this, or the one just multiplying x 10 times.
So again, 10 seconds, yes. Which is fastest? Oh, I get it. It does not show the timer when it's 5 seconds left. To keep the suspense.
And yes, most of you got it right. So here the performance is exactly the same. And so when we measure it, it's absolutely the same. Actually, when we have a look to the assembly, again, it's exactly the same. But there is some interesting stuff to discuss here. So first, we start with a loop. And usually when you write a loop, you might think that actually you would have a jump, just as the example we had before, where we had some jumps to actually do the loop, because that means you need to execute the same code, the same piece of assembly multiple times. But here we don't see any jump instruction or anything, like there is no branch in either of the functions. And as well, we can see 9 stars, but there is only 4 multiplications. And this is mostly due to the fact that the compiler knows that you're actually just multiplying the same number by itself 10 times, and it uses fast exponentiation, which reduces the number of multiplication. Because if you have a look to it, I mean, it's just the register names, but actually it multiplies x by itself, and then it takes this result and square it, which avoids doing multiple multiplications. And this is why actually there are only 4 multiplications instructions. And as well, we have loop unrolling, which basically boils down to exactly this, brings exactly the same code, but we're gonna come back to it. Now we have a similar example, but this time it's with an addition. So this code is adding to an input number, which is ACK. It's adding the sum of 0 to n minus 1 to this input number. So basically, this is what the initial loop at the top does. And so we have 2 implementations of this. The first one just in Rust using wrapping add, and the second one using inline assembly, because basically it does pretty much the same operation. And it adds to ACK the input number I. And so, again, which of those implementation is the fastest? Okay, oh, that was close. But yes, most of you got it right. It's the Rust sum. So, yeah, only 2, a difference of 2. But the assembly is not faster here, and we can dive in the actual results. So here with n equal 1000, actually the assembly is way slower, which is like a starting point. It seems really weird. And then if we run the benchmarks with multiple values for n, from 1000 to 10 millions, for example, we can see that it's completely linear. So basically it's in big O of n, so linear algorithm. Makes sense. There is a for loop. We do n time n iterations. But when we have a look to the Rust sum, it's not that linear anymore. It's just a flat curve. Always the same timings, 186 nanoseconds. And so the interesting part is when we try to understand what's going on. So here, for example, for the assembly implementation, most of what happens in the assembly code on the right is what you would expect. So at first you have some initialization, and then basically you have a jump if not equal. So basically this one here. Here you have a jump, and basically it's your loop. So expected n jumps almost roughly. So that will do n iterations. But when we have a look to the implementation, when you use Rust sum, so basically an idiomatic way of doing a sum, even if it's not really the most idiomatic Rust way to do this. Actually, what happens is really interesting because there is only one jump at the beginning, and it jumps basically when n equals 0. So it just, okay, the fast path, there is nothing to do, return. But otherwise, there is only like a bunch of operations, and it's only arithmetic operations. And actually, when we have a look to what's going on, the compiler figured out what we're trying to do, which is basically adding 0 plus 1 plus 2 plus 3 plus ... plus n minus 1, which can actually be simplified using the triangular sequence formula. And so it used this, and basically this is an explanation of this triangular formula, and you have the first terms, and we put a reference to the actual article about this. But the compiler figured out that this actually boils down to this, compiled it, and so now it just runs the function in a constant time. So whatever the size of the input, it will be 183 nanoseconds or something like this. So that's why this Rust implementation is faster than our inline assembly here.
Yeah. Next case studies, we're going to talk about bound checks. We have an algorithm that takes an array of integers, so use 32, and it's going to sum its elements. The first one is going to do a for loop on the slice, and both of them are going to do for loops. But on the first one, we are going to use the plus operator. And on the second one, we are going to use the unsafe, unchecked add operator. So for these two implementations, which one is the fastest? Nice. So yeah, it might have seemed like unchecked would have been a bit faster, or could be way faster, but no, they are definitely the same. And again, it's completely the same. So why are they the same? It's because actually, when we are using the release profile, so the bench profile is using the release profile, we do not have any overflow check. As you can see in the profile release, the default value of overflow checks is false. So it means that if overflow checks is false, it means that using x plus y is completely equivalent as using x plus unchecked add y in terms of performance. I mean, it's completely the same in terms of performance and also of logic, sorry. If we were using the dev profile, the overflow checks is true. So the difference between the dev profile with overflow checks true and the release profile with overflow checks false is that in dev, if we end up overflowing, the code will panic. And in release, if we overflow, the code will just wrap around the U32 without checking it. So just for the sake of understanding what's going on, let's change the overflow checks parameter of the release profile to true, and then rerun the same benchmark. I won't ask you what the result is, but we can see that it's a pretty huge difference. So this time, the unchecked version is way faster, 10 times faster as the normal plus sign version. So this is to show like the importance, like the performance impact of the overflow check. A bit of history. I don't know if you know about it, but all this stuff about integer overflow, it did cause some issues in production, and a pretty big one at that. I don't know if you're French or European, you might know about Adrien. It's basically a rocket that exploded because of that exact problem. So there was an inadequate overflow protection rule in the code, and it triggered a critical failure. And I just put a little bit of code to showcase what happens in release mode. So in release mode, if you don't really, if you use carelessly U32 and you go above the bound of the max of U32, if you just add 1 to U32 max, you will go back to 0. So in release, this completely works. So okay, it doesn't panic and it makes the code faster, but definitely in terms of logic, you can end up in pretty weird states. So really be careful about that. Of course, in dev, this would just fail, panic. Continuing with bound checks, now we are going to talk with slices. We have an algorithm that gets the max item of a slice. Same thing, we have an array, a slice of U32. Both are for loops. They are iterating over the size of the array, and they are accessing either the array directly with the access, the normal access operator, or the other one is using unchecked access to access the value. So out of these two implementations, which one is the fastest? Still some thought that unchecked access might still be faster, but no, it's still the same. And again, it's still completely the same. So why is it the same? It's because the compiler, again, is still way smarter than us. And the compiler is able to understand that we are using an iterator that is inside the bound of the slice. So it can prove that I, here in this loop, it's inside the bounds of the slice. So since it detects that, it will remove all the bound checks of the normal accessor. So that's why here we have this is completely equivalent with the get unchecked.
And so now a new case study on string concatenation. So here we have two different implementations, so with a lot of parameters, basically building a URL. And so it takes multiple parameters of your URL and it builds a string that will contain it. Two implementations, one using the format macro, and the second one using the plus operator a few times. So which is the fastest between those? Oh. And yes, this time the compiler is not that smart. And so basically performance, oh, I think there was a mistake. I think
should be plus.
Yes, yes. So
should be even
okay. So yeah, actually it's really 17 of you got it right, not 40.
Sorry for the for the 70 people that got it right, but yeah.
Issues. But yes, the performance is different. It's not that big, but still there is a gap. And we can actually explain this gap pretty simply, mostly because format might seem really optimized, but actually under the hood it's doing a lot of stuff. So basically first creating the arguments and then using dynamic dispatch to find the display method on each of those arguments, which is actually a lot of logic because the dynamic dispatch incurs quite big cost because we cannot really know which method will be called at build time. Then as well, overall, it just adds some abstraction layers. While using plus is pretty simple, we already know the type. And then overall, the compiler is not able to just optimize this format macro yet. Maybe someday it will come. But still, this implementation with the sum is pretty shitty because it's creating basically a new string instance all the time and allocating a new string object for all operators we can see, which can obviously be avoided because this makes a lot of allocations. And so we can have a more verbose version with, so basically initially we just compute the final capacity of our string. We do one single allocation on the heap, and then we just push on this string, allocating more memory. And so then if we measure the performance, so yeah, here, this is basically the detail of what I just said, allocation and then using push. And then if we compare the performance, this is way faster than the two others. But yeah, overall, for the initial question, plus was faster than the macro. Sorry again. And so now the results. So Seb E, where are you here?
Nice, congrats. Did you get the last one right?
Yeah. But yeah, congrats. Come see us at the end. We'll be able to give you a gift.
And yeah, if you got it right at the last, we're really sorry.
Yeah.
Yeah.
Now, if we recap on the learnings, as we saw in multiple examples, a lot of the optimizations were made by the compiler, and often trying to outsmart the compiler is not really a good idea, except if you actually measure. Then using const and const functions whenever it's possible, or trying to pre-allocate and avoid recomputation is as well beneficial. And then using inline assembly, even though it can look cool, sometimes it can just be an optimization killer. So when you're using it as well, make sure to measure and to analyze the final assembly that's generated by the compiler.
Yeah. another thing, as we saw, be really careful about integer overflow, because as we saw by default in release, they will wrap. Even if it's faster, they will wrap. And yeah, reallocating string is not that well known, but it's pretty efficient, as we saw in the last example. Like, the performance can really be increased. We saw that a lot in real world applications, where, for example, we had we saw a repo where they just were creating a I think it was stringifying some kind of struct into JSON, and basically they were computing the size of the string beforehand instead of allocating on the go, and it bumped the performance by really a lot. And one of the final word is that, yeah, before optimizing, as we saw, you cannot make really assumption about what's going to happen or what the compiler will or will not do. So the only way to be sure that you're actually going to have improvements or regressions is to actually measure what you are doing. And again, as we said, like, be careful about, you mentioned, just measure your code. And it bodes well that we tell you to measure your code, because that's what we're doing at CodeSpeed. So CodeSpeed is a dev tool that's aimed to make sure that you can measure the performance of your code directly in your CI, so that you don't have to wait to push your code to production to know about performance, regressions, or improvements. So we simplify everything to create those performance measurements and put it into your CI.
And we are really excited. We are really excited to support the open source communities and have a lot of cool open source projects using the tool. If you have an open source project, are interested in performance, really don't hesitate to come by the booth and talk to us. We'll be really happy to help. We can provide the infrastructure for free for measuring the performance and making sure that actually no release are creating harm on the performance of the overall ecosystem is really something we're interested in. And we already started doing this for a few years, so really excited to continue. And as well, it's completely free. Yeah. And so, yeah, come by our booth. It's in the hallway.
Yeah, right on the right when you get out. And to finish, so yeah, thank you for coming. And to finish, tonight, starting at 7, we are going to host a happy hour. Free foods and drinks will be on us. So it's a venue that's approximately 15 minutes by foot from the conference. It's a pretty nice walk down the canal. So yeah, we'll be really happy if you could join us. So yeah, just take a look at the QR code and register.
Or you can as well come by the booth. We can give you the info as well.
Yeah. So yeah, thanks all for coming. Thanks for, and I hope you enjoyed the quiz.